Yesterday we talked about phase diagrams. What do they show us? What do phase diagrams tell us? Okay, they show pressure and temperature, but what do they show us? What do they tell us? The phases, right? When you cross a line, what happens? You have a phase change, okay? So we went through, we detailed it out. It actually looked like this right here, right, where we drew that line in there. What did that line tell us? That red line, the dotted line. Standard pressure, which is atmospheric pressure. There's some term that is associated with that, which is called normal. Guys, normal means atmospheric standard pressure. Any of the values that could be given to you, right? If in your reference packet, it's referred to as standard pressure. So if it asks you for normal freezing point or normal melting point or something like that, that's what it is. You're looking at that standard pressure level. All right, so every time you cross the line, you had a phase change. Well, there's one other piece that we didn't talk about, we didn't get to yesterday, and that's this line right here. I would recommend highlighting it so you can see it or circle it or something, guys. But what is that line between? That line separates what two states of matter? Solid and liquid. Okay, so we've got solid and liquid in both of them. But are they the same line in each of these graphs? One's going what? One's going up, one's going down, right? One has a positive slope, one has a negative slope. That slope means a whole lot to us. It tells us two different things. Okay? And what it's going to help us figure out and relate to is density. Alright, is density. That slope, the difference in the slope, identifies or helps us to identify density. Now, it's not going to give us an exact value, but what it's going to do is give us some insight into which state of matter is more dense. Okay? Which state is always going to be the least dense? The gas state, right? The gas state of any substance will be the least dense because they're farthest spread out. So it's either going to be the solid or liquid state that's going to be more dense. Can you guys think of an example where the liquid state is more dense than the solid? Exactly, guys, water. Right? And that just happens to be one that's up here. What do you notice about the slope for water? It's down, right? So that's a positive or negative slope. It's negative, right? As you go from left to right, it decreases, so therefore you have a negative slope. So what conclusion can we make about the slope, guys? If it's negative, say it louder, Brent.
The liquid's more dense.
Exactly. So if it's negative slope, guys, the liquid is going to be more dense than the solid state. So here we go. So a negative slope means that the liquid is more dense than the solid state. On the flip side, if you have a positive slope, what does that tell you? The liquid is less dense. All right? You've got to know that. Negative slope, liquid is more dense. Positive slope, liquid is less dense. All right? Don't worry about the other lines, whether they're curved or not. Okay? It's that one line is the thing that's going to tell you. Now, does it tell you an exact density? No, it does not. Okay? But it just gives you some insight into which one is more or less dense. Okay? Questions about that? Make sure you know that for your test next week. Now, let's go ahead and talk about these vapor pressure diagrams. Vapor pressure diagrams. Actually, before we do that, let's go back to this page in your packet. We did not discuss, we went through all the questions yesterday except for the last two. We kind of left off there. And I'm not going to go back, guys, and put the answers up to those. The answers, we've talked through them, I explained them. Go watch the video from yesterday. It was at the very end of class. All right, but number 10 and number 11 we skipped. we didn't get to because we didn't talk about the slopes yet. So let's go through that now. It says, is the density of the solid greater than or less than the density of the liquid? What line are we looking at? This line right here. What type of slope is that? It's a positive slope. Which one is going to be? So that means the solid is greater than or less than liquid. Solid is going to be greater than. Greater than. It's a positive slope, therefore the liquid is less dense than the solid state. So we just wrote down. Now, number 11 is a little more challenging. You guys have to do something to figure this one out. It says, would an increase in pressure cause this substance to freeze or melt? So what two states of matter, guys, deal with freezing and melting? Solid and liquid, right? So you got to figure out a point where you're going to be able to cross the highlighted line because we have our solid state here, our liquid state here. So it says an increase in pressure. That means we're going to go what? Up, down, left, or right? Up, okay? Pressure is increasing as you go up. So that means an increase. We have to be able to cross the green line. So I'm going to draw a dot that's going to allow me to do that. To go from the solid to the liquid state. So I cross the line. Increase in pressure means this is going to go up to, say, this point right here. So what process does that show, guys, when I increase the pressure? I'm going from a what to a what? Liquid to a solid, which is freezing. It's freezing here. All right? If you're asked about that, or if you change a condition, all right, you've got to figure out and identify what two states of matter are being talked about in that problem. In this case, it was freezing or melting, so that's solid and liquid. All right, it said increase in pressure. What if it said increase in temperature? So that means pressure stays the same. All right, we pick a dot place here to say here, if we increase temperature, what process is that? Melting, all right? So that's kind of the way, guys, you would answer a question like that. Draw two dots in there, draw arrows between them. All right, the arrow will follow whatever condition they're putting on it in the question they're asking. Questions here? All right, let's talk about these vapor. What's that?
I'll say bless you.
Oh, okay. Let's talk about these vapor pressure diagrams. The last thing we got to talk about in our foldables. And where are they? In my opinion, it's just my opinion. You may have a different one, and that's fine. In my opinion, guys, these are the easiest diagrams to interpret because to me, there's the least amount going on. You've got three lines there. Those lines each represent a different substance. Okay, so typically you'll have a key like substance A, B, or C. So I'm going to highlight those in different colors. It does not matter what colors you use. All right. Then I'm also going to highlight this line right here. What is that orange line? Why did I highlight the orange line? Yeah, that's going to be our normal boiling point, right? Because normal means what? Standard pressure, standard temperature. Right? Okay. Then I've got blue. I've got green as well that I'm going to label. So this is my normal, which again just means standard. Normal pressure. So along here, guys, as the temperature increases, wherever that line, that orange line, the dotted one, comes in contact with your substance, what's that going to give us? That's going to give us our normal what? Normal boiling point, right? Because this is vapor pressure diagrams. So along these lines, those lines, guys, are showing you where those substances are vaporizing, aka boiling, right? Same thing as boiling. So now I have different colors here. We're going to label the different substances. They're going to show us kind of some different pieces of our substances. So these lines right here, these are my normal boiling points. Okay? Where those lines cross that pressure threshold, that 760 torr, standard pressure, that's my normal boiling point. Anywhere along those lines is where the substance is boiling, it's just the pressure is going to be different, and that results in a different temperature. Now, what we can look at, guys, with a vapor pressure diagram is that gives us some insight into their forces, how strong or how weak they're held together. All right? So, what forces hold molecules together? Intermolecular forces, okay? Which of those three substances do you think has the weakest intermolecular forces? Which color? Blue, right? Why? How do we know that blue have the weakest intermolecular forces? What do you mean by faster? Yeah, they boil at a lower temperature, guys. Absolutely. So, the blue means we have our weakest intermolecular forces. Green means we're going to have what? Strong. Strong intermolecular forces. Alright? So we're going to jot a note down right here. The higher the boiling point means the stronger intermolecular forces. We're going to jot another note down here. If you increase the pressure, you're going to also increase your boiling point. Right? This is why maybe when you guys have cooked pasta, if you read the directions, you have different cooking instructions for higher altitudes versus lower altitudes. Alright? Altitude, we know, right, is the height of how far away, how high above or below you are of sea level, correct? Alright? Is it easier, guys, to boil water at higher altitudes or lower altitudes? Before you answer that, think about which pressure is going to be higher. Lower altitude or higher altitude? What's that? Think about it like this. If you climb a mountain, what do mountain climbers take with them? What's one of the big things they take with them? Oxygen, right? Why? Why do they take oxygen with them? So they can breathe, right? Because what happens to the air as you get higher up? It thins out, guys. What is that basically telling us about the pressure? Pressure is going to decrease as you go higher in altitude, guys. The lower the altitude, the higher the pressure. So where is water going to boil faster? Higher altitudes or lower altitudes? What did we just say there? It says higher the pressure, the higher the boiling point. So higher altitude or lower altitude is going to boil faster? Higher altitude, because we just said...
You said the pressure's lower on the top?
Right. So is it going to boil faster? Yeah, exactly. Exactly. Right, guys, the higher the altitude, the lower the boiling point. So it's easier to get water to boil at a higher altitude. The lower the altitude, the harder it is, the longer it takes, the more energy it takes to boil water. Now, what does that do for cooking pasta? If you actually read the instructions, it takes longer to cook pasta at a higher altitude. Why? Because you're cooking at a lower temperature. Water will boil, guys, say at 90 degrees Celsius at a high enough elevation. Well, that's 10 degrees cooler than if you boil it at sea level, like at the ocean, at the beach. All right, it's going to boil at 100 degrees Celsius at the beach. So that means you're cooking your pasta at a higher temperature. It's going to cook faster. If you cook it at a higher altitude, like in the mountains, it's going to cook slower because you're cooking at a lower temperature. Does that make sense? Maybe you've never noticed it, but if you actually go and read pasta boxes, they have two separate instructions. One for high elevations, one for low elevations. All right. So, right here, guys, these questions you were supposed to answer. All right, here we go. Let's answer these questions. At what temperature would liquid A boil at an atmospheric pressure of 400 degrees torr? I'm sorry, not 400 degrees torr. 400 torr. That's a pressure, not a temperature. What's that? Why do you say 40, Brent? Exactly, guys. To answer this type of question like this, go to your pressure, draw a line across. Then for A, you're going to go down. All right, now it's a ballpark estimation here. So I would accept anywhere, guys, from about 30, I'd say probably 36 to 40 degrees Celsius. Okay? Liquid B should be right around about 70 degrees Celsius. And liquid C would be right around 100 degrees Celsius. How low must the atmospheric pressure be for liquid A to boil at 35 degrees Celsius? So how are we going to do this one? Right, you're going to start at temperature and then go up to where that hits the lines. So what you can do is draw a line at a temperature of 35. Again, you're ballparking it. Okay, something like that. Hopefully a little bit straighter than what I drew. All right, A is about what pressure? Somewhere I would say around 350. B, I would say somewhere around 175. And C, I'd say somewhere around 50. Again, guys, if it's a short answer problem on your test, there's going to be some wiggle room. If it's a multiple choice, you're going to pick the answer that best closely relates to what your estimation is. Number 7, what is the normal boiling point of liquid A? Normal means what? Standard pressure. So our unit here is torr. What's our standard pressure for torr? 760. So you're going to estimate 760 and go across. So for A, that's going to be right around 50 degrees Celsius, somewhere in that range. For liquid B, it'll be somewhere around 75 to 80. And liquid C would be somewhere around about 110. Okay? Now, question number 10, what we talked about with vapor pressure diagrams. Which liquid has the strongest IMF? Why C? It boils at the highest temperature, right? It's the one, folks, that is furthest to the right. That one is going to have the highest intermolecular force because it boils at the higher temperature. It takes a higher temperature for it to break apart. Questions?